Your book presents a discussion of the various modes of heat transfer, like conduction, convection, and radiation. There's probably one more that I'm dropping right there. But let's look at radiation. You don't really need to know the name of this law, Stefan-Boltzmann, but these names do show up in the labeling of constants pertaining to this law. And this is all about the intensity of radiation. We're talking about electromagnetic radiation emitted by a black body. So I'll talk about what a black body is in a second. But remember, this word radiate, it just means energy flowing outwards. And some radioactive materials actually emit material particles like electrons, or maybe I should say massive particles. When certain nuclei undergo beta decay, they can eject electrons. Sometimes alpha particles get ejected, which are helium nuclei. But we're just talking about radiated electromagnetic intensity, E&M waves, which you're familiar with from earlier in the semester. So let me just pick the easiest example, which would be a spherical star. If you could go up close to a star, and obviously this is not to scale, but just look at a 1 meter by 1 meter surface patch on that star. I picked 1 meter by 1 meter because 1 square meter is the SI unit of area. And if you could somehow measure the total power coming off of that 1 square meter, total power meaning the total number of joules per second, calculate, or not quite calculate, but measure how much total energy is emitted by this 1 square meter patch every second. That would be the number of joules per second per square meter. Here it is. It's an experimental constant, which I'll write down in a second, times T to the 4th power. This is the absolute temperature to the 4th power. So you can see immediately that the amount of energy coming off of this patch every second has an extremely sensitive dependence on temperature. Double the absolute temperature. Of course, that is a big temperature change, right? Because 300 kelvins is basically the temperature in which we live. 600 kelvins is too hot for any organism to live in. So doubling is a big difference on the absolute temperature scale. But if you were to double the temperature, 2 to the 4th power, I believe that's 16. An object that's twice as hot as it was previously would radiate 16 times the original power. That's a very surprising dependence on temperature. So this constant here, if you were to measure temperature in kelvins, which we do, then I'm going to put, for now, I'll put I for intensity because the units are watts per square meter. So the numerator, watts, that's power. We're talking about the concentration of power in space per unit area. So those are the units of intensity. This number here, it would be 5.67 times 10 to the negative 8th watts per square meter per Kelvin to the 4th power. That way, when you plug in your kelvins to the 4th power, those units cancel these, and what you get is the watts per square meter. And that's called the Stefan-Boltzmann constant. And check out how easy it is to memorize. 5, 6, 7, 8. Isn't that strange? It's like 3 of the most important people in my life, their birthdays are 5, 6, 6, 7, and 7, 8. And I have no problem remembering that because of the Boltzmann constant and because the numbers are sequential, of course. Okay, now this is really only true. This is only accurate in a lab for a so-called black body. So we all know, I think we all know, that black materials absorb more visible light than, for instance, white materials, like a white t-shirt versus a black t-shirt. If you've ever worn both of those on a hot day, in the middle of the day with a lot of sunlight, you've probably noticed that you feel warmer when you're wearing the black shirt than you might feel with the white shirt. Why is the shirt white? Because it's reflecting all the colors of the rainbow. We didn't talk about this in depth, but I think we all know at this point that white light is composed of all the colors of the rainbow. Of course, the human eye can be tricked into perceiving white light with only red, green, and blue. But if you were to shine all the colors of the rainbow into your eyeball, in other words, that continuous spectrum, you would perceive white. So most of the wavelengths get reflected by a white t-shirt, but a black t-shirt absorbs all of the visible light wavelengths. Now, that doesn't mean that a black t-shirt, like if I just scribble here. Pretend this is solid black. Okay, I'll make this a little easier for you. You may look at this and say, hey, it absorbs all wavelengths. Well, it absorbs all visible light wavelengths. I don't see green or blue, etc., coming off of this, but it's possible that it's reflecting infrared. We can't actually know that with our eyes. We'd have to use some other instrument. But if I were to hit this with a UV light, you might see quite a bit of reflected light. Well, if you had UV vision, right, like bees do. So just because it's absorbent in the visible part of the spectrum does not mean it's absorbent in X-rays, ultraviolet, infrared, etc. So a perfect black body, pardon me, a perfect black body would be one that absorbs light at all frequencies across the spectrum, and it would have 100% absorption. In other words, it's the blackest thing you could possibly think of. It won't reflect anything. And to help you visualize that, I'm going to go to a YouTube video. I'm just going to show a little bit of this video, but I recommend watching the rest of it. It'll help you conceptualize this business about a black body. The guy in this video, maybe you've heard of Vanta Black. Some laboratory developed a paint that's like the blackest paint ever. And he's actually dabbed some of that on a piece of paper. So you've got Vanta Black over here, or he calls it Black 2.0. I think it's related to Vanta Black. And then this looks like, I don't know, just a regular magic marker. And then over here, he's got something he claims is much blacker even than Vanta Black. Wait a minute, I thought Vanta Black was the blackest paint ever. Well, what he's actually done is take a box and poke a hole in one face of the box, and he's painted the inside of the box with Vanta Black. So any light incident upon this hole will pass through the hole, pass into the box, and then it'll bounce around the walls until most of it has been absorbed, so that practically none of it comes back out. And this may be a new concept to you, but the best possible black body you can conceptualize would be a cavity, in other words, a box with a hole in it. You really can't get any better than that. And that was the theoretical perfect black body when Max Planck first tried to explain the intensity profile of light coming from a black body. Because what I failed to mention so far is any material which is a really good absorber of light will also be a very good emitter. So I know I don't have a graphic for you, but supposing you had a black t-shirt and a white t-shirt, you went out in the middle of the day, you set them on the concrete, you let them both get warm. Let's say you brought them up to the same temperature, and then you take them back inside and set them in a cool, dark room. Which one's going to cool off first? Well, this might surprise you, but as I understand it, the black t-shirt would cool off the soonest, because it's going to emit infrared light and lose energy that way by virtue of being a good absorber. It is also, excuse me, a good emitter. Any material that absorbs efficiently will also emit efficiently. So you want to think about it in those dual terms. It goes both ways. So this is, again, this is a little harder to conceptualize, but the reason this looks so dark is because the light coming from within the room that this guy is standing in, that light is almost completely absorbed within the cavity. It doesn't come back out. But if we were to, you all know that the coils in a toaster, they glow red when they get really hot. A light bulb filament is just a skinny piece of metal that gets really, it radiates very intensely when it gets hot. If you could make the inside of this box super hot, it would also give off light, and it would do so very efficiently, just like it absorbs very efficiently. So that's kind of a silly thing to think about, but if you got all three of these spots up to the same extraordinary temperature, like 4,000 kelvins, this one would actually put out more light. This box would be emitting more light than these would be. Okay, let me just hit play on this. You can watch a few seconds.
Of light that it's absorbing, but it looks like it works okay. Okay, so we could not get any reflection with our 32,000 lumen flashlight. Let's see what happens when we shine a laser on it. So this is a 5-watt burning blue laser here. Now let's try it across my black that's blacker than Vanta Black. So here we go.
By the way, a 5-watt laser would instantly annihilate your eyeballs, so I would be really careful with those.
Here we go. Black 2.0, Sharpie, and my black. Nothing. Look at that. It essentially just goes away. You don't see any reflection at all. That's crazy. So what I have here almost perfectly mimics what we call in physics a black body. So a black body is a theoretical object that absorbs 100% of incoming radiation. And we know that this doesn't absorb 100%, but we saw that it was at least 99.99% of incoming light. And why perfect black bodies are important is because perfect black bodies allow us to calculate the maximum energy emitted by anything at a particular temperature. So if
Okay, which is exactly what we're talking about. You're wondering how this number was determined? It's measured. Now, I'm also sitting here wondering, can this law be not necessarily deduced in a laboratory, deduced in a laboratory? Could it be worked out theoretically? Could you look at the properties of atoms and somehow arrive at this conclusion? I imagine that's been done. I have not learned that myself, but remember, radiation consists of, we're talking about electromagnetic radiation, and it comes out at all different wavelengths. The sun puts out all the colors of visible light, in addition to infrared and UV. So there's a whole spectrum being emitted by this black body. And why do atoms emit electromagnetic radiation? E and M waves are emitted by accelerating charges. So the normal matter that we're familiar with, atoms, each of those atoms have electrons and protons, and it's the electrons which do most of the moving. And when they're jiggling around and transitioning between energy levels, that constitutes charge in motion. Well, not just in motion, but charge accelerating. So the accelerating charge of ordinary atoms is what's responsible for the electromagnetic radiation. So I suppose if you took a really submicroscopic view and applied quantum mechanics, perhaps somebody has explained why the surface of a material object emits radiation whose total output is proportional to the fourth power of the temperature. Now, since this law is on a per square meter basis, what if we'd like to find the total power being emitted by this object? For instance, the total power coming off of the sun. We would just take the power per square meter, which is called intensity, and then multiply that by the total number of square meters. So here's the way the law is usually presented. You still have your sigma, but then you have to multiply by the number of square meters times 2 to the 4th. And then there's one last thing we have to insert here. Again, this is the power radiated by a perfect black body. Well, what if it's not a perfect black body? What if it's not a hole cut into the lid of a box that's painted inside with Vanta black? What if it's just a piece of wood or a regular old piece of paper? There's no way that this thing emits power as efficiently as a true black body. So they stick this number in front called the emissivity. Emissivity, I believe it's dimensionless, and it's between 0 and 1. I put greater than 0 because I can't imagine it having no emissivity whatsoever. So this is something you need to know. And there's a number of interesting things we can do with this immediately. First thing I'd like to do is use this law to get a rough idea of what the surface temperature of planet Earth should be. And surprisingly, we're going to get a pretty accurate number. Here's the Earth, here's the sun. This is not to scale. The Earth is way smaller. It would just be a dot on the paper compared to a sun this size. And also, the actual distance between these two would not be the length of this paper. It would be more like a city block. Well, maybe not quite that big, but at least the length of our classroom. That would be more accurate. Okay, well, we've got power coming off of the sun, and we can easily calculate that power because we can determine the surface area of the sun. We can look up the sun's temperature, and we'll just model it as a perfect black body with an emissivity of 1. The surface of a star, I believe, is a pretty close approximation to a perfect black body. Again, that doesn't mean it's black. You know, if the surface of the sun were extremely cold, well, then it wouldn't be bright. It would look more like what you would expect a black body to look like. Now, some of that power is intercepted by the Earth. You know, a lot of these waves just completely miss the Earth altogether. But the area presented to the oncoming radiation by the Earth would be the area of this circle here that cuts through the center of the Earth. So I'll say area for the Earth would be not 4 pi, just pi times the radius of the Earth squared. That's the area of this circle here. That's how much power is intercepted, or that's the area through which the power is actually intercepted. Now, of course, it doesn't actually reach the center of the Earth. It's collected around the surface, but that ends up being the correct number. And here's the idea. Earth is not a perfect black body. It's actually fairly reflective. It has an albedo, you can look this up, an albedo of something like 30%, which means the ice caps, the cloud cover, all that water vapor, they reflect something like 30% of all the light striking the top of our atmosphere. So obviously not a perfect black body, but we can think of it as approximating a black body. So it's going to absorb all the light energy, or most of the light energy, coming from the sun. And if that were the case, if it just absorbed the energy and didn't emit it, then the thermal energy of the Earth would keep going up and up and up. In other words, the Earth would get hotter and hotter and hotter. But the hotter the Earth gets, the more it does what? The more it radiates. The higher the surface temperature of the Earth, the more power is being emitted by the Earth. So the Earth is doing two things. It's absorbing the light energy from the sun, which is most intense in the visible part of the spectrum. But then the Earth turns around and re-radiates a lot of that power back into space. And this is infrared radiation, infrared, because the Earth is not hot enough to emit visible light. Yes, the Earth reflects visible light. You can look up photographs taken from space, all you flat earthers, of planet Earth glowing beautifully in the expanse of empty space, but that's reflected light. So if you could turn off the sun, the Earth wouldn't look like that anymore. But the Earth still would glow. If you shut off the sun, the Earth's going to remain fairly warm for quite a while, and it really would shine in the infrared. If you had infrared vision, you could see the Earth shining. Okay, so here's the idea. As the sun hits the Earth with radiation continuously, and the Earth absorbs that radiation, the Earth would get warmer and warmer until it reaches a temperature such that it's radiating just as many joules into space every second as it's absorbing from the sun. So if it's shooting out just as many joules per second as it's taking in, then there's a net gain of 0, and the Earth would now have reached equilibrium. And presumably it reached that equilibrium a long time ago, and it's constantly adjusting. So we can apply that condition to figure out what the equilibrium temperature of the surface should be. Now, before I do this, mind you, we've completely ignored the greenhouse effects. In reality, there's clouds that blanket, well, not just clouds, but the atmosphere in general, which blankets the Earth, and that atmosphere is a really effective absorber of some of this infrared. So not all this infrared actually escapes out into space. It's absorbed pretty effectively by water vapor and carbon dioxide, and then re-radiated in part back to the surface. So it's a little more complicated than the analysis we're about to go through. So let's first look at how many joules per second are being absorbed by the Earth from the sun's light. I've drawn a giant imaginary spherical shell centered on the sun center, with the radius equal to the distance from the center of the sun to planet Earth. So I'm going to repeatedly apply this relationship, power equals intensity times area. We've looked at this before. If you take the total power coming out of the sun, and I can Google that, but actually I think we're just going to calculate that. Take the total power coming out of the sun and divide it by the surface area of this sphere. So that outgoing power, by the time it gets out to here, it's been diffused over that entire spherical shell. So it's much reduced in intensity. Okay, so the power received by the Earth would be the intensity of the sun's light at the Earth. We need the intensity of the sun's light here, times the area of the circle here, which would be pi radius of the Earth squared. Well, all we have to do is take the total power coming out of the sun, and I'm going to put this cool little symbol for sun. This is the luminous power of the sun divided down by the surface area of that giant imaginary shell, where this is the distance from the center of the sun to the center of the Earth. Okay, well, we can go even further because can't we calculate what the luminous power of the sun should be? I'll say, but the luminous power of the sun would be sigma, I'm assuming a perfect black body, so the emissivity is 1, sigma times the area of the sun, surface area, that's 4 pi radius of the sun squared, times the temperature of the sun to the 4th power, where I'm using the Stefan-Boltzmann law right here. This quantity is the surface area of the sun. Okay, so let me take this whole thing and plug it in there. So if I just write P, I'm talking about the power absorbed by the Earth. Let me stick all this in here now. Sigma 4 pi radius of the sun squared times the temperature of the sun to the 4th power. And it looks like some stuff is canceling here. That's good. Basically just the four pi's. Okay. Well, now let's look at the power radiated by Earth. This is what's absorbed from the sun by the Earth. And now, due to the Earth's temperature, much lower temperature, let's calculate the power emitted by Earth. Power, how about I put A for absorbed? Power absorbed, power absorbed. And the power emitted by the Earth. I'll just go with P sub E, power emitted by Earth, E for emitted, or Earth, whatever. Well, that's going to be Stefan-Boltzmann constant. Again, I'm ignoring the fact that the emissivity of the Earth is not actually 1. This is an approximation. Times the total surface area of the Earth, because we're looking at the power radiated by the entire surface area, 4 pi radius of the Earth squared times the temperature of the Earth to the 4th power. So if the Earth really is in equilibrium, the incoming absorbed power would have to equal the outgoing emitted power. Let's set those equal to each other. Set power absorbed equal to power emitted and figure out what that equilibrium temperature should be. And once again, keep in mind that we've completely ignored the greenhouse effect because that does complicate things. There's a great Wikipedia article about this. I can refer you to that. Okay, what's left in here? I'm gonna, let's see here. We've still got the sigma, the radius of the sun squared, temperature of the sun to the 4th power over D squared, and we still have a pi here, pi radius of the Earth squared. Okay, this is what I get by crossing everything out that I can here, and that must equal what's coming off of the Earth, 4 pi radius of the Earth squared, temperature of the Earth to the 4th power. And surprisingly, I'm finding that the radius of the Earth doesn't even matter. That's kind of surprising. So if Earth was a larger planet in diameter, it would still have the same equilibrium temperature? Okay. And remember, I'm solving for the temperature of the Earth. So what can I get rid of here? The sigmas go away. And I find that the temperature of the Earth to the 4th power would be, let's see, I'd have to divide by 4 on both sides. The pi's go away. So I've got radius of the sun squared over 4 times the square of the distance between Earth and the sun, all of that times temperature of the sun to the 4th power. Now I've got a book here that does a similar calculation, and I'll have to compare my answer in a second. Last thing to do would be to take the 4th power, or excuse me, the 1/4 power to cancel everything. 1/4, 1/4. Okay, so the temperature of the Earth should be, well, this is easy. T to the 4th to the 1/4. It's just that. And let's use the rule where we multiply powers. 2 times 1/4 is 1/2. So I've got a square root of the radius of the sun. And downstairs, I've got a square root of 2 because, let's see, this is 2 squared to the 1/4. That's 2 to the 1/2. So root 2, and downstairs root D. All right, so I guess I could have just written this as root radius of the sun over 2d times the temperature of the sun. Okay, I'm very relieved to find that my formula matches the one from the book. What book am I talking about? I highly recommend this. This book's been out for 10 or 15 years now. Physics and Technology for Future Presidents. That's a catchy title. This guy, Robert Euler. I think he was a relatively important physicist. You know, he's recent, so it's not like he invented quantum mechanics or anything. But this is an awesome book. It has a minimum of math in it, and it's kind of astounding the breadth of topics he covers, and he makes them really accessible. I had a lot of fun reading this book. Some of the fun topics in this book include the real story behind the Roswell UFO incident, you know, flying saucers in the desert. There's a perfectly reasonable explanation for that related to some topics in physics. He talks about the sound channel in the ocean. I don't want to get too much into a detour here, but there was a really cool program during, I think it was World War II, where if a pilot was downed, he could take these hollow metal spheres, drop them into the ocean, and when that hollow sphere got to just the right depth in the ocean, it would implode due to the great pressure and send out a sound wave which was trapped at a particular depth. So there's something called the sound channel way down in the ocean where, like, whale sounds, for instance, instead of spreading out in 3 dimensions, they're kind of constrained to move within a narrow range of depths. And as a result, the energy travels a lot further. So when these pilots were downed, the Navy had supposedly microphones set up in various strategic places around the ocean, and they could hear the sound of these little spheres being imploded and triangulate the pilot's position and go rescue them. So pretty ingenious. I haven't heard much about that outside of this book, but there's all kind of cool stuff in here. Highly recommended. Back to this calculation, I'm going to gather the numbers we need, and we'll see what the equilibrium temperature would have to be so that the Earth is putting out just as much power as it's absorbing. And actually, the only number I had to look up was the radius of the sun, because the others I know. The distance from Earth to the sun is 150 million kilometers. And the temperature of the sun, oh, I thought I had that memorized. It's close to 6,000 kelvins. But to 3 sig figs, it's 5780. Coincidentally, this temperature is very similar to the temperature of the filament inside a lot of incandescent light bulbs. So it's no surprise that the light coming off of an incandescent bulb has a similar quality to sunlight. They're both being emitted by materials with the same temperature. Okay, before I plug these numbers in, there's an alternate way of calculating the ratio R over D. If this is planet Earth and this is the sun, here you are on planet Earth. I'm going to use the Greek letter phi for the angular size of the sun. I've talked about how you can hold your pinky up at arm's length, and that spans about 1 degree in your field of view. Well, if you hold your pinky up and hold it next to the sun, obviously don't look directly at the sun. But if you had a filter, you would see that the angular size of the sun is about half the width of your pinky. So phi is about half a degree, 0.5 degrees. Well, let's convert that into radians. So let's convert that half a degree angular size for the sun into radians. Pi radians for every 180 degrees. What is the angular size of the sun in radians? I get 8.7 times 10 to the negative third. Well, remember, if this was the radius of a circle, and I called this arc length S, do you remember the relation between phi, R, and S? Phi would be S compared to R. And that's actually what we're talking about. I've chosen different letters here to remind you of the relationship from trigonometry, but this is the diameter of the sun, and this would be the distance from the Earth to the sun. So maybe I'll put capital D, and this is actually 2 times the radius of the sun. So when I go here to the formula, how perfect is that? The temperature of, the temperature of planet Earth, according to our calculation, should be the square root of radius of the sun divided by 2 times the distance. Well, how about I do this? And I'll stick in an extra factor of 2 here. So this would be 4D. Because this right here, this is the diameter of the sun divided by the distance from Earth to the sun. So I can just plug in that angle that we're already familiar with. Okay, so this would really be the square root of 8.7 times 10 to the negative third over 4 times the temperature of the sun. Let me calculate that. 8.7 times 10 to the negative third divided by 4. Then I take the square root and I multiply by the 5780 for the sun. And here's what I get, 270 kelvins. That's about right. 273 would be 0 degrees Celsius. So we're talking about 32 degrees Fahrenheit. And you know what? That's actually not a great value. It's ballpark correct, but I think I must have rounded considerably with this half a degree. I just wanted to show you that that worked. Let me go back and just plug in actual numbers here. So as a check, I'll just use this formula directly and plug in the numbers that, that I've written right here. So 696,000 kilometers, 696,000. I don't need to convert to meters because I've got another quantity down here which I'll enter in kilometers. So divided by 150 million divided by 2, I'll take the square root, and now I multiply by the sun's 5780 kelvins, and I get 278 this time. Okay, well that's 5 degrees Celsius. And let's lastly convert that into Fahrenheit, so times 9/5 plus 32, 42 degrees. I'm still getting a different number from what I expected. I thought it was supposed to be more like 80 degrees Fahrenheit, so I may have rounded one of these. But you get the idea. It's a livable temperature. It's above freezing. Now, when you take into account the Earth's albedo, in other words, its reflectivity, the fact that 30% of the light coming from the sun is actually reflected from the atmosphere, if you were to include that in the calculation, if we go back to power absorbed versus power emitted, here we go. Here's that sheet of paper. The power absorbed, I'd have to stick a 0.3 out front. Only 30% of what's coming from the sun is actually absorbed. If you would include that and solve for the equilibrium temperature, you would get a number here quite a bit below freezing temperature, which would suggest that the surface of the Earth would just be covered in ice and we wouldn't be here. So obviously there's something saving us from that, and that would be the greenhouse effect. The book that I just referred you to has a nice explanation of that. The other thing I'd like to do here with the Stefan-Boltzmann Law is to try to estimate the amount of energy that a human body has to consume, or a human being has to consume every day just to keep their body warm in order to maintain that 98.6 degree internal temperature. That's Fahrenheit. So here's my silly outline of, I traced this from something and the head still came out funky, but your body may not be hot enough, and I'm not talking about, attractive hotness, I'm talking about temperature. Your body may not be hot enough to glow the way the sun does. Obviously, that would be bad. You'd probably vaporize. But your body is warm enough to emit infrared. I think a variety of animals can actually see you in the dark because of the infrared radiation that you put off. So you do glow in the dark, just not at colors that can be seen by a human. And that's because your body temperature is not high enough. So let me draw some squiggles representing the power radiated by your body. Now, you're not a perfect black body, which is evident. All of us reflect some light, and we're probably pretty darn reflective in non-visible parts of the spectrum. But I have been told that the human skin is a really efficient black body in the infrared part of the spectrum. So regardless of your pigment, I think we all have similar absorption in the infrared part of the spectrum, which is why you can easily sense the heat coming from a fire. That's actually not conduction. The air is not very good at conducting heat from the flames to you. It's really the radiation coming from the fire that's being absorbed effectively by your skin. Okay, well, if we look at the, if we use this law, the Stefan-Boltzmann Law, and look up the surface area of the human body, it's an awkward shape to deal with because we're more complicated than just a sphere. Well, most of us. And we plugged in the human body temperature in kelvins and the Stefan-Boltzmann constant. And then you found the number of joules per second leaving the human body in the form of radiation. If you then multiplied that by the number of seconds in a day, you would find that you'd have to eat, I forget, I just ran the numbers a minute ago and it was like 10,000 calories, 20,000 calories a day, which just sounds way too high. So that was kind of naive of me to calculate that. What that tells you is if you were naked in outer space with no air surrounding you, yeah, you would be losing energy really quickly. Of course, then you'd stop using energy because you would be dead in short order. But we're walking around bathed in air. Now, air is a very poor conductor. We still haven't talked about conduction. That'll be the next video. So we don't actually have to worry about the heat whisked away from your body by conduction because air is a poor conductor. Water, on the other hand, is a much better conductor. We only have to worry about the radiation. But keep in mind that the air which surrounds you, here's my little, to represent air, and the air is right next to your skin. I'll use a marker now. It's also radiating energy at your body. So your skin is simultaneously emitting oops, that was supposed to go into the body. It's simultaneously emitting radiation by virtue of the body's surface temperature, but it's also absorbing energy from the surrounding air. And that should help you understand why the net rate of energy transfer, and here I'm going to use dq dt. I believe your book uses that. That's the number of joules per second. Q represents heat. So this is not thermal conduction. This is a transfer of heat using electromagnetic radiation. Let's just assume that both emitters / absorbers are perfect. So we'll go with an emissivity of 1. And I can factor out the sigma A. And we'll go with T of the air to the 4th power minus T of the body. I'll put T of the skin to the 4th power. So this first term represents the heat flowing into your body because your skin absorbs what's coming out of the air. And conceptually, I've always found this a little bit challenging, and I think I'll save that discussion. But you just have to imagine that you're tightly clothed in a layer of, let me put it this way. If we're talking instead about a sphere, it's emitting radiation due to its own temperature, but the air around it meets it at its surface. So you can almost imagine, instead of the sphere, imagine the negative of the sphere, so to speak. It's like, what if this circle just represented everything outside and a cavity within? So instead of thinking of this circle here as the boundary of the sphere, think of it as the boundary of a cavity, and the walls of that cavity are radiating inwards. So this is like the air radiating into your body, whereas this is the surface of your body radiating outwards. And the net rate of energy transfer would just be the difference in the two. So I've used a positive sign here because this is heat being absorbed by your body. The negative sign accounts for the fact that we've got energy leaving your body. And since the temperature of the skin is usually higher than the temperature of the air, then this quantity will come out negative. And that means there's a net flow of heat out of your body. That's the case, of course, if it's very cold outside. We all know what that feels like. We feel the heat leaving our body. On the other hand, if the air was hot, if you were in Death Valley and it was 115 degrees Fahrenheit outside, this quantity would actually be positive. So would that suggest that your body's total energy would be rising? I mean, that would very, very quickly make you sick and then kill you, so that your body would have to have some way of shedding heat, and that's what the perspiration is all about. Then you're talking about heat of vaporization. So I guess your body's got a couple mechanisms here for losing or shedding thermal energy, just the radiation and of course also sweat. Okay, let's calculate these things. Let's go with an air temperature of 20 degrees Celsius. That's room temperature. In other words, 293 kelvins. Now I looked up a couple numbers online. Firstly, we need the temperature of the human skin. I know that your internal temperature is supposed to be something like 98.6 Fahrenheit, but we're talking about the power radiated by your epidermis. So I Googled that, and evidently there's a range of values depending on which part of the body you're talking about. So I'm just going to go with a temperature of 95 degrees Fahrenheit. I'll write that down. Temperature of the skin is 95 degrees Fahrenheit. Let me first convert that to Celsius. So I'll take 95 and subtract 32 first, hit equals, and then multiply by 5/9. So 35 degrees Celsius, and that'll put us at, hang on a second, 35 plus 273, that'll put us at 308 kelvins. And then I'm going to need the surface area of the human body. You could try to estimate that yourself, but good luck with that. If you were shaped like a sphere, that would make things easier. Well, it would make that easier, not other things easier in life, but let's just Google that value. Of course, the surface area will depend on the individual, but I've seen this number before in physics books, actually, so we'll go with that 1.7 square meters. Okay, I'm going to plug those numbers in, and we'll see how many joules per second net are entering, or in this case, leaving the human body. So first I'll do the quantity in parentheses. If I take the 293 kelvins and raise it to the 4th power, and then I'll subtract the 308 kelvins raised to the 4th power. That's a big old number. Raising a number to the 4th power, it gives you a very large number. And then I have to multiply by the 1.7, so the order of magnitude, that doesn't change anything. But here's where the number gets brought far down. Multiply by the Stefan-Boltzmann constant times 5, 6, 7, 8. Love that. And I find negative 157 watts. Interesting. Now, your body doesn't just need energy to stay warm. It's also got to rebuild tissue. I'm assuming grow new tissue, all the electrical stuff that's happening in your nerves and your brain. I really don't know much about it, but I'm guessing that the majority of the energy that you consume is really just to keep your body warm. That's got to be the most costly aspect of being warm-blooded. Well, most of us are warm-blooded. I can't speak for a couple ex-girlfriends there, but let's now figure out if this is how many joules are being used or are being lost by the human body and must be replaced every second. How many would we need per day? So the total energy per day would be dq dt times the total time interval. So I'm going to go with 157 joules every second. And that's like the wattage of a couple light bulbs, right? That sounds about right. Times 24 hours times 3,600 seconds for every hour. That's an H right there. Let's see just how many joules we're using every day to stay warm. Okay, can I put this in scientific notation? 1.36 times 10 to the 7th joules. Whoa, that sounds like a fantastic number, but don't forget, one nutritional calorie is 4190 joules. So drum roll, please. 4190. Okay, I'm gonna round that down to 3,200 calories. Hey, that sounds familiar. I think a lot of us consume 3,200 calories a day, whether we need it or not. It's still on the high side, right? Because I'm just talking about keeping your body warm. I'm not talking about running the 100-meter dash a few times that day, or running half a marathon, or even just walking around your house, walking back and forth from the couch to the refrigerator. This seems a little on the high side. So I got to thinking, what's up with that? Because all the numbers I plugged in were valid. And what I came up with is the following. this would be accurate if your body was shaped like this. What a boring life that would be. But if this was your topology, yeah, all the energy that's radiated from this space, it's not coming back, and same for the bottom face. But the actual topology of the human body is more interesting. So if you think about it, a lot of the power being radiated by your inner leg here would just be absorbed by the other leg. It's kind of bouncing back and forth. And certainly that's true in your armpits. When your arms are down, you've got a significant amount of energy coming off your torso that would just be absorbed by your arm and vice versa. So I don't think you're actually losing this many joules every second. And if you made a correction to that, you probably would come down to the typical, let's say, 1,800 calories per day. This is the reason why people can sleep near each other to stay warm, right? Animals in the wild do it. People do it because if you have two bodies next to each other, a lot of the power lost by your body is absorbed by your neighbor and re-emitted. Just like a blanket. A blanket does the same thing, and the atmosphere does the same thing for the surface of the earth. Way to tie it all together there, huh?